Thank you, Eric. As my presentation slide shows, I'll be talking today about our signing and marking practices and specifications that we use here in the state of Texas. I'll go over some of the specifications we have for traffic markings, the practices we utilize for traffic markings. Then I'll discuss some of the specifications for signing products, and then go over some of the history that was involved with our development of our signing specifications and the standards that we use for signs. And then I'll review those revisions that we made to the material specifications and standard sheets for signing products. And if I get through this quick enough, maybe have time for some questions. So these are the specification items that we use for traffic marking. 666 is the big one for pavement markings. That's one that's utilized most often. 668 is for tape products. Raised pavement markers is item 672. If you want to use a multipolymer, which is your epoxy traffic markings or polyurea traffic markings, that's under a special specification at 6473. And then we're using retroreflectivity data now. We're rolling that into the specification books, and the specification for that governing the data collection is special spec 8094. You can see the various material specifications for the traffic products and the plan sheets. So in Texas, for our concrete roadways, our high volume concrete roadways, we recommend you use the multipolymer products, the epoxy traffic markings. Tape is often used, although you'll pay a lot more money to use tape than the epoxy markings. And some profile is used as a edge line, but not a lot of profile is used on concrete. And then our asphalt roadways, it's primarily thermoplastic. We're a huge thermoplastic state. One of the largest users in the world of thermoplastic. We do use some traffic paint, but it's primarily thermoplastic. And then profile thermoplastic for asphalt roads is really, our use in the last 5 years has grown because of the rumble strip applications. You can use profile for that. So one of the reasons why we use so much thermoplastic is in Texas, our roadway texture is so coarse. The surfaces, our seal coat rocks are much larger than what's used in other states. And so what that ends up happening is you get a very highly texturized surface, and that affects the retroreflectivity ability of that stripe. And when I say retroreflectivity, that's a term referring to the ability to shine light back to the light source, or in this case, back to the driver. So the deeper the texture, the larger the texture, particularly you have a gap-graded grade 3 seal coat, the less retroreflectivity you're going to get from the stripe. So you need to fill in that stripe with thermoplastic material, and that's why we specify a minimum of 100 mils thermoplastic. Here on this, right here, you can see we've got two different stripes here. One's at 80 mils, the other one is on the bottom here is at 120 mils. And you can see the 80 mil stripe is very, very texturized. You can see some rock and texturization in the 120, but it's much less minimal than this. And then the retroreflectivity at 6 months, you can see the difference here. And it generally, this isn't as indicative of the difference that you can get as you fill in the valleys. You can get much greater retro performance differences as you fill in those valleys. One of the things I wanted to point out was you can see this stripe here. It's a very canary yellow type color, and then this one's more of an orange yellow. Well, this is an older stripe when we used lead chromate as the pigment. Lead chromate is a very stable pigment, and it can maintain this canary yellow performance even at night in retroreflectivity. Whereas this is an organic pigment. Organic pigments are less opaque at night, so you had less of a yellow color. In other states, when you see an organic yellow that starts out like this in the day, if it looks canary yellow in the day, it'll be very white at night. So ours start out very orange in the day, but at night you get much more of a yellow color to it. So that's why the color difference. So in Texas, again, we generally specify 100 mils on new thermoplastic markings. That's for seal coat surfaces. And that's a minimum of 100 mils. I mean, oftentimes a contractor is going to have to put down, 110, 120 to really fill in the gap, the valleys of a seal coat. For retrace, we're at the standard 60 mils. We are rolling in retroreflectivity performance requirements into the 2014 spec book. These values, if you're familiar with what other states use, are much lower than what other states typically specify, and that's, again, take into account that our roadway surfaces are much more texturized. And so they're set at a lower value to be measured at 3 to 10 days. And then we specify what's called an AASHTO type 2 and 3 beads, which are medium-sized beads. If you're familiar with what other states use, a lot of times they'll use what's called an AASHTO type 4, which is a very large bead, and an AASHTO type 1, which is a very small bead. But they contend with snowplow, and the thinking is the 4 and 1 blend works better for snowplow operations. Whereas we found in Texas the 2 and 3 combination works really well on seal coats. But we do have, so this is being rolled into the 2014 spec book. Again, this is lower values than what's typically specified in other states if they specify retro. We do have a new specification out, Special Spec 8999, that has much higher retro performance values. These are 250, 175, 3 to 10 days. The performance values on this spec is 400 and 250 after 30 days. So it's much more stringent. We took out the bead requirements. The contractor can use any bead system he wants as long as he meets these. So much more stringent requirements, much higher performance. And the districts that have utilized this specification have found that the contractor can meet these, but typically he's having to use an extruded or a ribbon applied thermoplastic and not a spray applied, which provides a much thicker, uniform applied stripe. So you do have this option in the special specs. So we're rolling retroreflectivity into this construction book. The spec governing the data collection is Special Spec 8094. There is a handbook of best practices on the traffic operations website if you want to look that up to see how what to do with the data collection. All mobile units must be certified by TTI. They have a certification program. This is the actual certification deck that the units must drive, and then they must be within 15% of the handheld readings. And then we don't allow handheld. The contractor only has the option to use a handheld retroreflectometer for data collection on jobs of less than 200,000. I guess that's 200,000 linear feet. Okay. So when you do, under the data collection, typically the mobile units will continuously collect data and average it every 1/10 of a mile, and then that mile, those 1/10 of a mile or 1/10 of the mile averages are averaged over a mile, and that mile segment that's what has to meet the minimum retro. To help out certain situations, we've got some guidelines. So we don't want a situation where 50% of the data is under a mile average is below and 50% is above, but the average is above. We don't consider that passing. And so if more than 30% of the data within a mile average is below specification, then it's not supposed to meet. And then the opposite end of things, if you've got a segment of roadway where the mile average, if you were to throw out 20% of the data, you would have a passing mile, then we say go ahead and accept that. And that's to take into account situations where you might have a turnout or a construction zone or something where you're just not able to keep very good markings. You can go ahead and just accept it off of that. And then we try to define what a 1 mile segment is. it starts at the first data collection point when you start your data collection, and it moves at discrete 1 mile increments from there. We were having situations where the contractor wanted to move that mile, and so he can adjust that mile, and it makes it easier for him to pass segments that you might think would fail. So under the signing specifications, 636 is the big one for aluminum signs, and then you have 644 and 647 for the large and small roadside signs. The material specifications, the big one is DMS 8300. That covers your sign sheeting materials and EC film and screenings. And then the standard sheets, you have your TSRs and your DNOMs. Under DMS 8300, you have various types of sign sheeting materials. Here you got a picture. Right here is the old engineer grade sign sheeting product. Cities still use this product. DOTs no longer use that since it's a very low performing product. And it wouldn't meet, this product does not meet the new federal mandate requirements. So this has been phased out of DOT use. The next generation of reflective sheeting product was it's still a beaded product, but it's called beaded high intensity, and you can see the honeycomb patterning. So this was about 10 times brighter than this material. And then the next generation from that, which is what we're into now, is called prismatic. And you can see that these utilize beaded microscopic beads for the retroreflectivity, and this uses microscopic prisms. And so you have various different types of prismatic type sheeting products. The designations of these were designated under ASTM as they were rolled out, as the new product was rolled out. So this was like a type 3, ASTM type 3. This was an ASTM type 4. And then these came in one after another, ASTM type 7, 8, 9, 10, 11. They've consolidated several of those types now. Now you have just 8, 9, and 11. Now there's a new sheeting spec on ASTO we developed, and you have type A, B, C, D, which kind of incorporates all these. So you have the different types of retroreflective sheeting. They came on the market at different times. Again, we started out with engineer grade, went to beaded high intensity. They were both beaded products. The performance of the products amongst manufacturers was very uniform, was very similar with each other. We didn't really see any differences in the performance. The prismatic products started coming out, and they're very directional. Depending on how you rotate the prisms on the sheeting. And so we started seeing stuff with the prismatic products that we weren't seeing with the old beaded products. And some of this stuff was, you might have noticed some of this. So in the daytime, you might get the sun hit the sign at a certain angle, and it'll just glare, bloom like crazy. Over here we have, this is a beaded high-intensity background, green background with cut-out white prismatic letters, and on the bottom is a white prismatic background with green EC film, and the letters are cut out of the green EC film. And you can see that the white prismatic background is just flooding, washing out the green EC film. Over here, if you can see, you're wondering where where the missing letters are. The letters are there and they're actually functional, but the human eye autocorrects and autofocuses to the brightest object within its field of view. And so these letters here they were nested, and when the sign was fabricated, and so they were rotated, and again the prismatic products are highly directional, and so when you rotate them to the human eye, the reduction in retroreflectivity makes it look dead. And then over here, similar to this issue, if you certain signs, if you have, particularly if you have brights on it, you can get so much light return, it washes out the message and causes a glare. So we're having these issues with the prismatic products that we weren't having with the beaded. And so we wanted to look into, well, what's going on and how can, we define a specification to address some of what we're seeing. The ASTM specifications, they were derived basically as a QC tool, quality control tool. So that, as the products were rolled out of onto the market, particularly the prismatic products, it wasn't the performance tables that you measured the products against weren't derived based on what a driver needs or what a driver experiences with that product. It was based on, well, this is how this product performs at these angles, so you can tell if the product was manufactured correctly. And there's two angles involved in this performance measurement. One's called the entrance angle, which is the angle incident to the object from the light source, and the observation angle, which is the angle from the object back, the light source and the object back to the observer. And so with those two angle sets, you define certain performance characteristics of a product. Well, those performance characteristics, again, under ASTM, had nothing to do with what a driver needs or how a driver views a sign. And so, we were looking at that and we were like, well, how can we define a specification based on what a driver needs or what how the driver experiences that sign? And maybe if we did that, maybe we could better define the products we're using and try to address some of these issues that we were seeing, because all those issues I highlighted before, all these products pass specifications. These products, this is not a failed product. These are all passing products, but we're getting these issues with material that meets specification. So one of the things you need to know about signing materials in driver performance behavior is a driver takes, research has shown that a driver takes 3 looks at a sign. So you have your look 1, which is your detectability distance, is when they first notice that there's a sign there. They're too far away to read the sign, but they first notice that there's a sign. The second look doesn't really convey any information. The driver's just rechecking the sign, that the sign is there, and he's coming up and he's going to need that message. And the third look 3, the driver's coming up on the sign, and that's when he actually looks at the sign to obtain the message, whatever that message is. So we understand some of the driver performance behaviors with the sign, and the angles that the ASTM tables were set at this angle. And so the sheeting performance for the products are set at the detectability distance. And so there was a push in an industry to keep making signs brighter and brighter and brighter, and to make them brighter at this angle set, which is the detectability distance. So you can see the sign from further and further away, which is basically looking at the sign straight on. Versus when you're up actually reading the sign, you're at a much higher angle. And so oftentimes you would have, especially the early generation prismatic products, it would be very bright at this detectability distance, so you could see it from really far away. But once you got up to this legibility distance, the sign brightness would drop off dramatically. And the other feature that we knew from driver performance was, or from research on human performance, was that an object, the brightness of an object increased. The necessity for the brightness of the object had to increase exponentially for the human eye to detect it. And so at very low light levels, it doesn't take a lot of brightness increase for the human eye to see that there's a difference. But as that object gets brighter and brighter, it takes a lot more light for the human eye to register that there's a difference in performance. And so we took that human performance curve with the eye and brightness levels, and the fact that this is the legibility distance, this higher angle set is when you actually look at a sign to read a performance. And we got with other states who were seeing similar issues with their signs and TTI, and decided, hey, let's form our own specification. So we went through AASHTO and tried to derive a specification that was more driver performance based, and with the intention of, hey, if we can have a specification that's more geared toward what the driver needs, then we can better define the products that we want and how we use those products. So here's a chart showing retroreflectivity performance differences between the different types. AASHTO came out. Again, there were various types under ASTM, 4, 7. There was as much as 7, 8, 9, 10, 11. They consolidated those down to 3 under the prismatic. AASHTO, it's just 4 sets. The type A, they started with the beaded high intensity, which was that honeycomb beaded pattern. And they went up from there using the human performance I curves. The type B, type C, type D. Manufacturers are not comfortable warranting their product to a type C. So essentially the market is broken down into type A's, type C's, and the type D's are the new, what's called full cube prismatic. It's the new DG cubed and OmniView prismatic products. What we noticed when we looked at the sheeting performance versus these tables that were derived under AASHTO, we saw that, you know, at this detectability distance, you get these huge values. But again, it leads to, particularly with white signs, it leads to these glare issues. And then we notice down here, these values down here, these are the higher angle sets, and these angle sets represent your legibility distance as a driver in a car, and then these angle sets over here represent what a truck driver sees. And I don't know if you can see this, but this green and the purple is type C and type D. Again, there are very few of products on the market that are warranted as a type C. And then the type D are the new full cube prismatic. Well, you can see that they're the only ones that perform or provide any retroreflectivity for a truck driver. So essentially all the signs we have out on the roadway right now are basically dead to a truck driver because we weren't utilizing the type D products. And so, you know, seeing how the different products perform under the new specification kind of gave us an idea of, you know, what we'd want to use for certain signs. Again, I mentioned earlier, you know, some of the glare issues. So we were seeing this in some of our signs, particularly when you get in a rural setting and you put your high beams on. And I make mention that it was characterized as discomfort glare because in all the previous research that had been done, they had never identified that it actually lowered the legibility or detectability distance of the signs. So there wasn't a lower performance associated with these signs or the glare, but it was in all the research people would identify the sign as too bright. Too bright, it was bothersome. So they always characterize it as discomfort glare versus disability glare. But we thought, is that true? Is that the case? It never really been. We had never done a study to identify, well, is this truly discomfort or is there any sort of disabling component to these signs? So we commissioned TTI to do a study to look at it. Do these signs affect driver performance in any way? And what they did was they put objects in the roadway. This is a deer right here. So it's a fake deer. They had this fake deer, they had a little box, and they had a human stand on the side of the road, and they would have different drivers drive and see how far away they could detect that object in the roadway with different types of sign products. And what they found was, yes, the brighter the sign, particularly when you're driving with your okay, I'm getting close. When you're driving with your your bright, what's it called? Your brights on. It does affect your ability to detect an object in the roadway. And so with that, we understood. Okay, yes, signs can be too bright, particularly in a rural setting when you have a white regulatory sign. And so we revised the specifications. We did a quick study to make sure that what we found was in the lab, we saw that the beaded high intensity products performed at the legibility distance angle set equal to the prismatic products because there was enough of a difference. The retroreflectivity dropped enough on the type B sheeting products that the performance was the same. And so there was no performance loss if we were to just go and say, hey, look, let's just specify type A because we're not having this glare issue with the type A. it doesn't affect the signs. And so what we did was, okay, we understood that the Type D products is the only products that work for a truck driver. Well, our truck drivers are on our freeways, and so we changed the standard sheets to incorporate Type D prismatic legend for our freeway signs, which is your overhead signs and your large ground mounts. And we changed all the regulatory signs to Type A, which is was just the beaded high-intensity products on the market. We've had recently a manufacturer submit a prismatic version of Type A, which has been approved, but it's a much lower performing product. So you don't, when you're in a rural setting, you won't have this disability glare issue with it. And then we did some other changes. In the specification, we're now referring to AASHTO instead of ASTM. And because the Type D comes with a longer warranty, we incorporated that into the sheeting specification. We made several other changes. So I think I've been kind of belled. So if there are any questions, I've got a couple of minutes to answer any questions.